16b people, this is probably more specifically for the Merck's people. Here is an arc length and a surface area problem. So with the same function. So I want to find the arc length of y equal to x cubed over 12 plus 1 over x for x between 1 and 2. And I feel like the green pen might be kind of hard to see with the lighting. Let me darken through it a little bit. I think that helps a bit. Yeah, it's a little too dark. So the way you're finding the arc length is you're integrating from a to b of what we usually think of as ds, where ds is either the square root of 1 plus the derivative of your function of x squared, or it's the derivative, or it's the square root of 1 plus the derivative of your function of y squared, or it's the derivative of the dy dt squared plus dx dt squared. In this case, since we have a function of x, it's going to be the square root of 1 plus our function of x derivative squared. And you write this as dy dx squared, you can write it as f prime of x squared, whatever. And now the way this should typically work out is my derivative squared should have a negative 1/2 in the middle. And it exactly will. If I look at dy dx here, dy dx is, let's see, the derivative of x cubed over 12 is 3x squared over 12. And the derivative of 1 over x, which is x to the negative 1, is negative x to the negative 2. This simplifies as x squared over 4, minus 1 over x squared. And if I square this out, well, I get the first thing squared, so I get x to the 4th over 16. I get the first thing times the second thing times 2. X squared over 4 times negative over x squared is just negative 1/4, so I get negative 1/4 twice, so I get negative 1/2, which is what I'm expecting. Again, right? This times this is negative 1/4, and another this times this is another negative 1/4, so negative 1/4 plus negative 1/4 is negative 1/2. And then I get plus 1 over x to the 4th, because negative 1 over x squared times negative 1 over x squared is 1 over x to the 4th. And then if I add 1 to this, right? So if I add 1, I'm going to get x to the 4th over 16 plus 1/2 plus 1 over x to the 4th, which is factor exactly the same as this, except the middle sign should change. This is going to be x squared over 4 plus 1 over x squared quantity squared. So what ends up happening is this integral here ends up looking like the integral from 1 to 2 of the square root of this, right? Because that's 1 plus the derivative squared. The square root of something squared is just the inside something, really an absolute value, but we're going to disregard that because everything is already positive. So this is going to equal, let's go down here. Sorry, this is going to equal way over here the integral from 1 to 2 of x squared over 4 plus 1 over x squared dx. And now we can integrate. The integral of x squared over 4 is x cubed over 3 times 4, which is 12. The integral of x to the minus second is x to the minus first over negative 1, or minus 1 over x. So when all is said and done, after you've taken your function, taken the derivative, squared it, added 1, taken the square root, and integrated it, you essentially end up with the exact same function you started with, except with the sign in the middle has changed signs. And really this happens like all the time. So we end up with plugging in 2, I get 8 over 12 minus 1/2 minus plugging in 1 over 12 minus 1. And simplifying that, 8 over 12 minus 1 over 12 is 7 over 12. And negative 1/2 plus 1 is positive 1/2. So you get 7 twelfths plus 6 twelfths, which is 13 twelfths. So that's how long this function is for between x equals 1 and x equals 2. So now we're going to look at the arc length of this thing rotated around either the x-axis or the y-axis. So this looks like something, right? I don't know exactly what it looks like, but I can try and graph a little bit of it. Right, if x is 1, I get 1/12 plus 1, so I get like 13 twelfths, which is just coincidental that it happens to be what that is. So when I plug in 1, I get a little bit more than 1. And when I plug in 2, I get 8 twelfths plus 1/2, which is 8 twelfths plus 6 twelfths, which is 14 twelfths, so not a lot bigger. So I don't actually know if it's getting, it's probably looking something like this. So looking at something like that. And then we're going to rotate it around the x-axis. and see what kind of surface area we get. And then we're also do the same around the y-axis. Okay. So, when you revolve around the x-axis, or any axis really, the way I always think about the surface area is it's the integral of 2 pi r times my ds. ds is still that square root thing, and r, the radius, is how far away we are from the axis of rotation. If we're going around the x-axis, how far away we are is how high up we are. So we think about the radius as being the y value. So I can do the integral of 2 pi y times ds, but y is equal to this function. And since it makes sense to do things in terms of x, to find the surface area here, I'm going to do the integral of 2 pi times f of x times my ds, which is the square root of all that junk. So in this case, it ends up equaling the integral from 1 to 2 of 2 pi times my function, which is x squared, x cubed over 12, plus 1 over x, times, we already know that the square root of 1 plus all this is, well, here is the square root of 1 plus all this just ends up being x squared over 4 plus 1 over x squared. I know it's kind of quick. I'll talk about it. I can say that again. Right, I'll just say that again, right? If I'm doing this, if this is my ds, ds is the square root of 1 plus this squared. Here's the 1 plus this squared, which is just this. And if you take the square root of that, you're just back to x squared over 4 plus 1 over x squared. So going around the x-axis in this case, you get the integral of 2 pi times your function times your ds. And then it's going to be a little bit gross. I'm going to erase up here so I have room to write out what the integral actually is. So I'm going to end up getting, I'm going to bring out the 2 pi. Multiplying this out, I get x to the 5th over 48. The numbers are not going to be nice here. And then I get x cubed over 12 times 1 over x squared is x over 12. And then I get 1 over x times x squared over 4, which is x over 4. I should probably put this together as x over 12 plus 3x over 12, which is 4x over 12, which is x over 3. Let's do that. And then 1 over x times 1 over x squared is 1 over x cubed, or x to the negative third. Integrate. We get x to the 6th over 6 times 48, which is 240 plus 40, which is 288. We get x squared over 6. We get x to the negative 2nd over negative 2, which is minus 1 over 2x squared. And that's x to the negative 2nd divided by 2. From 1 to 2. And then we plug in, and things are gross. 2 pi times 2 to the 6 is 64 over 288. I'm sure that reduces 4 over 6, 1 over 8, minus, when you plug in 1, you get 1 over 288, that's gross, plus 1 over 6 minus 1 over 2. Let's not simplify that and just say we did. I'm sure it's not fun. I'm sure this reduces because, yeah, that's just arithmetic. It's terrible, but you can do it. I was talking about going around the y-axis. So if I go around the y-axis, it's still the same beginning integral. That's the integral of 2 pi times the radius times ds. If you're going around the y-axis now, the distance to the y-axis from wherever you are isn't measured by y, it's measured by x. So 2 pi times x times this ds is actually what we're going to calculate. In this case, since we're doing things in terms of x, we don't change it to some function of y, we leave it as x. So if things are in terms of x, around the y-axis your radius is x, around the x-axis your radius is y, which is f of x. If you happen to be in terms of y, then things are flipped. So here, this one's actually less terrible. That's the integral of 2 pi times x times still the same ds, which is x squared over 4 plus 1 over x squared. So that's less terrible. I'm going to erase some stuff so just we can calculate it. Yeah. Again, I always say, so for arc length, I'm always starting off with the integral of ds, which is just the square root of whatever. For surface area, it's the integral of 2 pi r times ds. So here we're getting 2 pi times the integral from 1 to 2 of, multiply out the x, it's x cubed over 4 plus 1 over x. It's going to be interesting when you get a natural log. So integrating this, I get x to the fourth over 16 plus the natural log of the absolute value of x, 1 to 2. 2 pi times plug in the 2, I get 2 to the fourth, which is 16 over 16, plus natural log of 2. I don't write the absolute values because I know 2 is positive. Minus, plug in 1, I get 1/16 plus the natural log of 1, which is 0. So I end up getting 2 pi times, 16 sixteenths minus 1/16 is 15 sixteenths. So I get 2 pi times 15 sixteenths minus the natural, plus the natural log of 2. And I would probably leave it like that. So there is some arc length and surface area. It's kind of gross, I'm not going to lie.